Welcome back to Explained, where we break down complex topics and try to make them, well, a little easier to understand. Today, we're going to take a deep dive into hash tables, which are pretty fundamental data structure in computer science.
Yeah, you're right about that. They really are everywhere. Like, think about it. Every time you search for something online or even just open an app on your phone, hash tables are kind of quietly working behind the scenes to make it all happen as quickly as possible.
Well, okay, now that's got me interested.
That's
So let's start with some basics here. I've heard about dictionaries before in programming. Is that where hash tables come into play?
exactly. Dictionaries are all about storing information and being able to find it again really quickly based on a specific key. Think of a real dictionary. You use a word, the key, and you can find its definition. Hash tables are like a super efficient way to implement those dictionaries.
Oh, I see. So it's like having a librarian who knows exactly where every single book is, right?
Uh,
No more wandering around those stacks for hours.
Yeah, that's a great analogy. And that's really the beauty of hash tables. They let us achieve what we call near constant time complexity, meaning finding, adding, or removing data takes pretty much the same amount of time regardless of how much data you actually have.
It sounds pretty impressive.
Yeah.
But how do they actually pull that off? What's the secret behind all that?
Well, the secret's in something called a hash function. It's basically a mathematical function that takes your key and then it transforms it into an index, a specific location in the hash table. So that index tells us precisely where we need to go to store or find the data.
Okay, so if I'm following you, the hash function is kind of like our super organized librarian, right? Just points us directly to the right shelf.
Precisely. And that's the beauty of it. This super fast mapping from a key to an index is exactly what makes hash tables so efficient. But there is a slight catch. What happens when two different keys end up with the exact same index?
Oh yeah, that does sound like a problem. It's like trying to fit two books into the same exact spot on the shelf.
Exactly. And that's what we call a collision. And this is kind of an unavoidable problem when you're working with hash tables. But don't worry, there are some really clever ways to actually handle these collisions.
Okay, all right, I'm listening. So how do we prevent things from completely falling apart when those collisions happen? How do we handle those?
So one very common approach is called separate chaining. So imagine that each index in our hash table, it's not just a single slot, but it's actually a chain, almost like a linked list. And so if two keys map to the same index, well, we just add both of the data entries to that chain.
Ah, okay, so instead of fighting for the same spot, we just kind of extend the shelf to make room for both books.
Exactly. Now, another method is coalesced chaining, and this is similar to separate chaining. So it uses the hash table itself for the overflow, but with two different regions in the array, an address region and an overflow region.
Hmm, clever. So if the main parking spot is taken, we just park a little further away, no problem. But I'm guessing there are more ways to solve this whole collusion problem, right? I mean, there's got to be.
You're exactly right. There's another popular approach called open addressing. So instead of using chains, we actually calculate different alternative locations within the hash table itself. And this happens if that first index is already taken.
Gotcha. So if the shelf is full, we just start looking for the next available spot.
Exactly. And there are different ways to do this probing. One is linear probing, where you just move to the next slot in the table. Then there's quadratic probing, which takes a bit of a more sophisticated approach, taking kind of bigger steps to avoid clustering. And finally, there's double hashing, using two different hash functions to try to find that empty spot.
Okay. Double the hashing, double the fun, I guess, right? But, thinking about it now, all of this really depends on having a good hash function in the first place, doesn't it? I mean, even the most talented, organized librarian can't find a book if that cataloging system is all messed up.
You're absolutely right. Designing these effective hash functions is really the key to making the entire hash table perform well. So you want a hash function that's fast, it minimizes collisions, and it spreads those keys uniformly across all of those indices. It's like trying to organize this massive library where every book has the absolute perfect spot.
Well, that sounds like a pretty tall order to me.
That's
So how do we even start designing these magical hash functions? What are some common techniques that people use?
Well, there are some kind of classic techniques that are very common. One is using the modulo operator, where you just divide that key by the size of the hash table, and you use the remainder as the index. And another approach is multiplication, where you just multiply that key by a constant to try to get the index.
Okay, so it's really all about just transforming those keys into indices in a clever way, right?
Yeah.
But are there any potential problems that we should watch out for when we're doing this?
Yeah, that's a good point. You always have to be careful. because the hash function that you choose can have a big impact on performance. For example, if you use that modulo operator, it can be really sensitive to the size of your table, and it can potentially lead to more collisions if you're not careful.
Okay, so it's not just about picking any random function. It's about finding the right tool for the job, I guess.
Exactly. And that brings us to a cool concept called universal hashing. So instead of just sticking to a single hash function, what we do is randomly pick a hash function from a whole family of functions. And we do this every time we make a hash table.
Hold on, wait a minute. So we're adding some randomness to the mix now. How does that actually help?
Well, imagine it's like shuffling a deck of cards. You can never be quite sure which card's going to come up next. And this randomness that we introduce, it makes it much harder to predict and exploit any weaknesses in a particular hash function. It's a powerful technique that improves the overall reliability and security of our hash tables. But now, what if we're not just working with simple numbers as our keys? What if we're dealing with things like strings, sequences of characters?
That is a good question. Strings are just everywhere in programming, and they can get really long and complex, so how do we even begin to hash something like an entire sentence? Don't forget to follow Explained for more deep dives into topics just like this.
Well, there are a few approaches. One is to treat the entire string as just a really big number and use some of the techniques we already talked about, like modulo or multiplication. But this can be pretty computationally expensive, especially if those strings are super long.
Yeah, that makes sense. It's like trying to fit a whole encyclopedia onto a single little shelf.
Right. So another way is to break down the string into smaller chunks, hash each of those individually, and then combine those results in some way. And this is generally a more efficient way to handle those longer strings.
Oh, okay. So it's like creating a bunch of little mini indices for each chapter of the encyclopedia instead of trying to index that whole thing at once.
Exactly. Now, one really interesting technique for string hashing is called Horner's method. And this method was specifically designed for what's called efficient polynomial evaluation.
Hold on, polynomials. That sounds a little scary. Can you break that down a bit for me?
Sure, so think of it this way. A polynomial is a mathematical expression with multiple terms, and each term has a variable that's raised to a power. And so Horner's method is just a really clever way to evaluate these polynomials, but using the least amount of computation, making it a perfect fit for calculating these hash values for strings. Because remember, efficiency is key here, especially when we're dealing with lots of data.
So I'm hearing that Horner's method is like finding the shortest path through a really, really complex maze.
That's a great way to think about it. And that's why Horner's method is so commonly used for string hashing.
Okay. This is all starting to click now, but so far we've just been talking about hash tables in a very general way, in theory. I'd like to get a little more specific. How are these ideas actually put into practice in a real programming language?
That's a great question. So let's take a look at Java. This is a language that uses hash tables a lot. In Java, we have the HashMap class, and this provides a really powerful and flexible way to implement hash tables. Have you ever wondered how your computer can instantly find a contact in your phone's address book? Let us know what you think down in the comments.
The hash map. Yeah, that rings a bell from my coding days. Can you tell me some of the key things about how Java implements these concepts?
Sure. So Java's hash map, it gives you a lot of control over the hash table. You can actually set what's called the initial capacity. This means how many buckets it starts with. And then you can also set the load factor. And this basically determines how full the table can get before it automatically resizes itself.
Well, that's interesting. So we can kind of fine-tune those settings based on our specific needs, depending on how much data we're actually dealing with.
Exactly. And when it comes to handling those collisions we were talking about earlier, Java's hash map, it typically uses separate chaining with linked lists.
Right. Okay, so each bucket's basically a linked list that can just hold multiple entries if those collisions happen. We covered that, right? But is that all there is to it? I feel like there's got to be more to it.
Well, in Java 8 and later, things got even fancier. So if a bucket starts getting too full, then that linked list is actually replaced with a tree structure. And this is done to make the lookups even faster.
Wow, so Java's constantly evolving to make hash tables even more efficient. It's like they never stop trying to improve.
Exactly. They're always innovating. Another really cool thing about Java's hash map is how it optimizes that index calculation we talked about before. So instead of using that modulo operator, which can be kind of slow, it leverages what are called bitwise operations.
Wait, bitwise operations? Now we're getting really into the weeds here.
I know, but it's super clever. Java basically uses these low-level tricks to make those hash tables super fast.
So it's all about just squeezing every little bit of performance out of those hash tables, huh? But I do think it's really important to clear up one common misconception. Hash tables, while they do involve hashing, they're not the same as what are called cryptographic hash functions, right?
You are absolutely right. It's really important to understand that difference because cryptographic hash functions like MD5 or SHA, they're all about security. So they're used for things like verifying passwords or making sure that messages haven't been tampered with. Their whole purpose is totally different.
So even though they both use the word hash, they're playing in completely different ballparks.
Exactly. Hash tables are all about efficient data retrieval, right? But cryptographic hash functions, those are all about security, these one-way transformations. Okay, so let's go back to Java's hash map for a minute here. There's this one concept that's just super important when you're using custom objects as keys, the hash code and equals methods.
Okay, I remember those. Can you unpack that a little for us? Why are these methods so important when we start working with our own objects, our own custom objects?
So in Java, every object has these two methods, right? Hash code, which calculates an integer, a hash code for that object, and then equals, which basically compares that object to another object to see if they're the same.
Okay, yeah, that sounds kind of familiar. But can you remind me again why these methods are so important when we're using hash maps specifically?
Well, when you go to use a custom object as a key in a hash map, Java actually relies on the hash code method to figure out which bucket to place that object into. And then it uses the equals method to see if that key already exists in that bucket.
Gotcha. So they're kind of like Java's way of handling our custom objects as keys correctly, right?
Yeah.
But what happens if we accidentally mess up how these methods are implemented?
Ooh, that's where things can get tricky. Because if hash code and equals aren't implemented correctly, you can end up with these sneaky bugs that are very hard to find.
Yeah. Uh-oh, bugs. That's never good. Can you give me an example of what could go wrong, something specific?
Sure, imagine you have two objects that represent the exact same thing. For example, let's say two-person objects with the same name and the same age. Now, if you don't override hash code to consider these attributes, these two people might end up in different buckets, even though they should be treated as the same key.
So even though they're logically the same, they end up in different parts of that hash table.
Exactly. And that can lead to all sorts of weird, unexpected behavior. Like, you might try to retrieve data using one of those person objects as a key, but the hash map can't find it because it's actually looking in the wrong bucket.
Oh, that sounds like a debugging nightmare. So the key takeaway here is to be super careful when you're implementing hash code and equals for those custom objects, right?
Absolutely. And when you're implementing them, be very mindful of which attributes of your object you're actually including in that hash code calculation. You should really only stick to attributes that are part of the object's core identity and are unlikely to change over time.
So we want to avoid using attributes that are, fickle, attributes that might change unexpectedly.
Exactly. And using objects that can change after they've been created, what we call mutable objects, as keys, can also cause a whole bunch of other problems. Because if the object's state changes, its hash code might change too. And then it could end up getting lost in the hash table.
So immutability is our friend when it comes to hash table keys.
Got it.
But we can't forget about strings. Earlier, we talked about how hash functions handle those in general. But how does Java specifically approach string hashing?
So Java uses a clever variation of Horner's method, that efficient polynomial evaluation thing we were talking about earlier. And it does this to handle that string hashing. It's all about trying to be as efficient as possible when dealing with those sometimes very long strings.
So Java's bringing all that efficiency we were talking about to string hashing. But I imagine even with all this cleverness, collisions can still happen with strings, right? There's no way to completely avoid them.
Yeah, that's right. Collisions, they're just an inherent part of hashing. No matter how sophisticated our hash functions are, there's always the possibility of a collision. It's like a fundamental challenge that we have to deal with.
So it's all about trying to minimize collisions and handling them gracefully when they do happen.
You got it. That's really the essence of how we work with hash tables. You're right. It's almost like we're rolling the dice a little bit with those collisions, even if we have a really great hash function. The more entries we have, the more likely it becomes that two keys are going to end up with the same index.
It makes me think of that saying, if you have enough monkeys typing for long enough, they'll eventually produce the complete works of Shakespeare, right? Give those collisions enough time, and they're bound to happen.
Haha, that's one way to put it. But the good news is we have those collision handling techniques we talked about earlier to keep things organized, even when those metaphorical monkeys get a little too productive with those keys.
Exactly. Those chains and probing techniques are like our trusty backup plan when things start to get a little crowded in the hash table. Speaking of crowded, let's shift gears a bit and talk about why our listeners should even care about all of this hash table stuff. How do these concepts actually show up in their everyday lives?
Well, you can think of hash tables as kind of the invisible scaffolding that's holding up a lot of our digital world. I mean, think about all the apps and services we use every single day. Social media, online shopping, those search engines, they all rely heavily on hash tables to manage huge amounts of data and retrieve information incredibly fast.
So every time I'm searching for something on Google or just scrolling through my social media feed, hash tables are quietly working behind the scenes, making sure everything runs smoothly.
Precisely. Hash tables are the reason we can get those lightning-fast search results and even those personalized recommendations. They're even used in things like password management systems, making sure that all your sensitive data is stored securely.
It's amazing how these data structures, which seem pretty abstract at first, have such a huge impact on our digital lives. They're like the unsung heroes of the internet, aren't they?
I like that, unsung heroes, working tirelessly behind the scenes to make sure everything runs as it should. And, as we all use more and more data-driven applications, hash tables are just going to become even more important.
We've been talking a lot about how Java implements hash tables with its HashMap class. But are there other ways to approach this? Do other programming languages handle hash tables in completely different ways?
Oh, absolutely. Java's HashMap is just one example. Plenty of other languages have their own built-in support for hash tables, and each of them comes with its own quirks and optimizations. It's a bit like different philosophies for building and organizing a library.
So the fundamental ideas behind hash tables stay the same, but the details of how they're actually implemented can differ quite a bit depending on the language and what it prioritizes.
Exactly. Some languages might really focus on using as little memory as possible, and that's memory efficiency. Others might prioritize raw speed, trying to squeeze out every ounce of performance from their hash tables. And then you have languages that are designed for systems where lots of processes need to access the hash table at the same time. That requires some pretty complex techniques to make sure the data stays consistent.
That's fascinating how a data structure as simple as a hash table can be adapted and refined to work in so many different environments. It really shows just how flexible and powerful they are.
Yeah, and it really highlights the creativity and problem-solving skills of all the people in the computer science world. I mean, even with something as fundamental as a hash table, there's always room for new ideas and ways to make things better.
Well, before we move on, I think it's time for a little recap for our listeners.
Yeah.
What are some of the key things we've learned about these fascinating hash tables today?
I think the most important takeaway is this. Hash tables are incredibly efficient for storing and retrieving data when you have keys to work with. And they achieve that efficiency through the clever use of hash functions to transform those keys into unique indices, along with those collision handling techniques to manage those cases where multiple keys happen to map to the same index.
Right, so we talked about separate chaining, using linked lists to handle those collisions, and then open addressing, where we basically search for the next open slot in the table.
And of course, we had to look at how Java's HashMap actually puts all of this into practice. We talked about how it lets you control things like the capacity and load factor of the hash table, and even its use of tree structures to boost performance in certain situations.
And we even took a detour into the world of string hashing, learning about Horner's method, that technique for calculating hash values for strings efficiently.
And we discovered that no matter how clever our hashing techniques are, collisions are just an inherent part of the game. So we always need to think carefully about how to minimize them and how to handle them gracefully when they do happen.
Well, I feel like we've only just scratched the surface of this topic today, but I hope this gives our listeners a good foundation to build upon.
Me too. I love these deep dives into the fundamental concepts of computer science. It's like we're getting to see the inner workings of the digital world, right?
Absolutely. And as our world becomes increasingly reliant on all these data-driven technologies, understanding these fundamental ideas is more important than ever. But before we wrap up completely, I want to leave our listeners with a little challenge. Now that you know a little bit about hash tables, see if you can spot them in action as you go about your day in this digital world. Think about all the apps you use, the websites you visit, the games you play. I bet you'll be surprised at how often hash tables are quietly working behind the scenes to make it all happen.
That's a great challenge. It's like suddenly having a whole new way to look at the digital world, isn't it?
I have a feeling we're going to get a lot of messages from our listeners about all the hash tables they've discovered. But seriously, it's amazing how fundamental and impactful these data structures truly are.
It really is a testament to their elegant design and their efficiency in solving a very basic problem, how to organize information and access it as quickly and smoothly as possible.
Well said. And with that, I think we've come to the end of our hash table adventure for today. It's been a pleasure exploring this topic with you.
The feeling is mutual. I always enjoy these conversations about the essential building blocks of computer science.
And a huge thank you to all our listeners for joining us on this deep dive. We hope you found it both informative and, dare I say, a little bit fun.
Well, if it's fun, then you know people are learning something.
Exactly. If you enjoyed this episode of Explained, and you have some ideas for future topics we should cover, we want to hear from you. Be sure to leave us a comment down below. And of course, don't forget to follow Explained for more deep dives into the world of science and technology. Till next time, happy hashing, everyone. Yeah, I bet you're right. Once you start looking for them, you'll be amazed at how often they show up.
It's true. They're one of those really fundamental concepts, but they have this huge impact on how things actually work.
Speaking of how things work, we talked a bit about how Java uses that HashMap class to implement hash tables. But are there other common implementations out there? I'm curious about what other languages do.
Oh, definitely. Different programming languages have their own ways of doing hash tables, and of course, each one comes with its own advantages and disadvantages.
So it's kind of like choosing the right tool for the job.
Yeah.
Right. Some implementations are going to be better for speed, maybe some are better for memory efficiency, and so on.
Yeah, that's a good way to think about it. Some languages are designed to keep the amount of memory they use as small as possible, and this is really important if you're running an app on a device that doesn't have a lot of memory. And then there are languages that are made for systems where lots of processes need to access the hash table all at the same time, and this leads to more complex implementations that make sure the data stays safe and consistent.
It's amazing to me how these simple data structures, like hash tables, can be adapted and tweaked to work in so many different situations. It really shows you how flexible and powerful they are.
For sure. And it's a testament to the creativity and problem-solving skills of all the amazing people in the computer science community. Even with something as fundamental as a hash table, there's always room for new ideas and ways to improve.
Okay, before we wrap up today's deep dive, let's take a minute to recap what we've learned. What are some of the key things about hash tables that our listeners should take away from this?
Well, I'd say the most important takeaway is this. Hash tables are all about speed and efficiency when you need to store and retrieve data based on keys. And they get that speed and efficiency from those clever hash functions, which transform keys into unique indices, and then, of course, those collision handling techniques that we spend some time talking about.
Right, we covered separate chaining, which uses linked lists to deal with collisions, and then open addressing, where we basically just go searching for the next available empty slot in the table.
And we even had a chance to look at how Java implements all of this with the HashMap class. We saw how it gives you a lot of control over things like the size of the hash table, how full it can get, and how it uses tree structures to boost performance in certain cases.
It's really impressive to see how much complexity is involved in making these seemingly simple data structures work so well.
It is. And as our world relies more and more on data-driven technologies, understanding these fundamental concepts becomes even more crucial.
That's a great point. Well, this has been a fantastic deep dive into the world of hash tables. I always learn something new when we explore these fundamental topics in computer science.
Me too. It's a good reminder that even the most complicated systems out there are built on these elegant and powerful concepts.
Absolutely. And a huge thank you to all our listeners for joining us on this journey today. We hope you found it insightful and maybe even a little bit fun.
Fun is a good thing. It means people are engaged and learning.
Exactly. If you enjoyed this episode of Explained and you have any thoughts on what we should cover in future episodes, please leave a comment down below. We love hearing from you. And don't forget to follow Explained for more deep dives into the fascinating world of science and technology. Until next time, keep exploring, keep learning, and maybe you'll start to see hash tables everywhere you look in the digital world.